Hello, welcome to a chapter about ideal gases. So this was just all about gases, but in this chapter we're going to look at two main ideas: the behavior of gas. How do you describe and predict it? Now there are two main areas. The first one, which is what this video is about the macroscopic behavior of gas. Macroscopic means the large scale one, the what we call observable, like you can see the gas do this. You can observe with you can measure it with a gauge or something like that. The thermometer, measurable. Okay, so these are all what we call macroscopic. Other things is we will study about ideal gas laws. You may have heard of this before or may not, but there are Boyle's law, Charles' law, and a few others. We combine them all together. And there is also we're going to look at what we call empirical and experimental analysis. So we're going to look at experiments you can do on gases lah, right? So experiment analysis. Now it's a bit hard to do experiments here, but actually there are things you can do at home. Anyway, an overview is in the later part of this chapter 10, we are going to look at the microscopic. So we're going to zoom in into the gases and see each gas particle, how they behave. What we're going to study what we call Brownian motion, how the particles fly around, gas particles. We're going to talk about the kinetic theory of gases. Ooh, so this is like a kind of a cross link to chapter 12. It's kind of like a chapter 12 topic as well. So this of gases. And lastly, we're going to talk about statistical analysis. So these gases are very small. We have to use statistics and probability to understand what they are doing, how they behave, what is their property. Okay, so these are two ideas of that. On macroscopic, what are the things we're going to study? There are some quantities that we will be looking at a lot, and that is, tada, a whole list of them over here. So we have seen most of these things before. Some may be new. Gas pressure. Oh, we're going to use the symbol P. This would be in units of pascals. Okay, so this is what we call one of the quantities that we'll study a lot. Volume, we'll be usually measuring in meters cubed. Temperature, oh, this one important. In this chapter, we treat temperature in Kelvin, absolute temperature, right? Absolute pressure, absolute temperature. Number of moles, well, this is a new thing, okay? N is like number of moles, all right? The mole is just how much amount of gas there is, or how many particles are there in a certain area. Okay, there's a specific number, don't worry, we'll see that later. And usually we calculate this with the mass of gas lah, okay? So this mole is a new thing. It's also a SI unit, kind of. But what is happening here on the microscopic end? Oh, we'll study different kind of quantities and they look very familiar. You're like, wait a second. Velocity of gas particles, momentum, kinetic energy, and potential energy. Now this sounds like kinematics from AS. Yeah, it's very interesting because you're going to treat every single atom as like a ball that is colliding with something, flies here, flies there with a certain energy. So yeah, that is what we're going to learn all about in this chapter. But let's start off with a thought experiment, or rather a gas experiment here. If we go to the left, you notice here there are three laws that we'll be looking at in this video: Boyle's law, Charles' law, and pressure law. What is Boyle's law? Let's start with this one first. So Boyle's law, people did experiments once upon a time, and they played with the pressure and volume of a gas. What did they hold constant though? They held constant the temperature of the gas. So they keep the temperature in the container the same. And of course the number of moles lah. Number of moles, which is N. Now how does this experiment look like? Here's an example. This is an example of a container. There's no gas in there. That's why you see the pressure gauge here is 0. But what happens when I start to add in some gas? So I take this pump and go pss, pss, pss. Okay, then you see the gas particles will spread out. This is in slow motion lah, okay? The moment you pump in, they should all be spread out nicely. So this is when they're all bouncing around happily. And you notice the pressure is about 2000. Temperature, 300 Kelvin. Now what happens if I increase the volume of this container 2 times? What do you think happens to the pressure? Okay, notice the pressure up there is about 2000. If I increase the volume 2 times, the pressure will drop half. So volume is 2 times, the pressure become half, and the temperature is still kept constant. Why is that so? You notice these particles, how they behave? Okay, let me go back to the beginning. When it's this, they are hitting the walls of the container much more because they have lesser space, they're flying around. If I increase, they're like, wow, a lot of space to fly, so they hit the container lesser. So this is one observation that people made, and it's named after this fella, Boyle's law. So since the temperature is constant, like just now we saw, no change in temperature, the kinetic energy of the particles is also constant. Now this is the idea lah. What is temperature, kinetic energy? Okay, so constant, they're moving around. But when the gas is compressed, like just now I squash the container, the volume decreases. So when there's a smaller space, what happens to all the particles? There's more collision between the gas particles and the walls of the container. And when there's more collision, then we say gas pressure increase. So this is a throwback to the animation that you just looked at. In fact, I'll encourage you to hit the link down below and also go and play with it yourself to see for yourself what is this law about. So what's happening here is, what are we changing? Pressure, volume. You change the volume, then you see the pressure change. Okay. So we can create a law, Boyle's law, out of this thing. So we know that when pressure increase, let's change it with terms of volume. So when volume decrease, pressure will increase. That is what we call an inversely proportional relationship. So the Boyle's law, we can say, okay, P is proportional to 1 over V. Ta-da! But, there's constant, right? Okay. So we have a constant here, which is temperature, but don't worry about that. We can do ratios. From one state to another state, you can say that the ratio of P, V is the same. So you can say this ratio from pressure of 1 equals to volume of the first one, second one, volume of the first one, and something like that. You might be saying, Miss, where this come from? The inversely relationship here. I just put them all together, ma. So you can rearrange this to something more convenient. So P1 V1 equals to P2 V2. And this is one of the ways you will be calculating changes in gas. Okay, so maybe they'll say, oh, at first the volume is like this. Then you decrease the volume, it becomes like that. What is the pressure? Okay, that is one example lah. So it's important to note that for Boyle's law, the temperature is constant. So I put a reminder here. Temperature is constant. Okay, so if we were to plot a graph of P against 1 over V, how should we do that? So here's a graph. Well, it should be a straight line because, P proportional to 1 over V. So I will attempt to draw a straight line graph. Yeah, something like that. Okay, so if you have a gas at a certain initial volume here, you can change it to a certain volume here. You have a different pressure, 1 over V. Okay, so that's how you can record that lah. So P1, P2 is corresponding to 1 over V1 and 1 over V2. There's also another type of curve that we'll usually plot, and that is called the PV curve. Now the PV curve is very convenient because we're going to use this for all the laws. You will see a PV curve for everything. But if you want to plot P against V, that's an inversely proportional relationship, right? So your graph will look something like this. Curvy. Yeah. Okay. So from here, you can also do something like that. Okay, if you have an initial P1 that is up here, that will correspond to a certain volume, V1. If you have a certain pressure, let's say down here, okay, over this part, you correspond to a second volume, V2. Like the animation we saw just now, okay, you have a volume, you suddenly increase, it becomes very big. Now, when you're doing that, something that you should note is that the area under the PV curve is the work done. So I will highlight this area. There we go. So this area is the work done, either by gas or on the gas. Throw back to AS. PV, So this is work done by gas or on gas. You see, when you're trying to compress the container or stretch out the container, you're gonna do work, changing volume. Okay, so that's one thing to note. Okay, back to this graph. Something to note also, if you're at a higher temperature, your curve will be a little bit different. So this one is assuming that your temperature is same all along this curve at 300 Kelvin, for example. I don't know, I just choose a temperature, okay? So at every point on this curve, you have the same temperature. What if your gas have a different temperature leh? Then how will the curve look like? Still inversely proportional, but it will be at a higher place. So up here, for example. Wow, a bit hard to draw leh. Okay, I try my best. Okay lah, whatever. So this one will be at a higher temperature, 400 Kelvin, for example. So the work done will be different already lor, because different area ma. Okay, so that's the first thing you need to know about Boyle's law. Boyle's law is temperature constant, PV equals to PV. How about the other law? You may have guessed. So what is Charles' law? Like what did this Mr. or Mrs. Charles do? Well, Charles' law is talking about what happens when you play with volume and T. Wow, magic words disappearing. So if V and T is what's changing now, these are the variables changing, what else is to be constant? Pressure lor. So pressure have to be constant. I write out the whole thing. Pressure P is constant. And overall, of course, moles, number of moles of gas, how many particles are there, should also be kept constant. Okay, kind of something like that. So what is the experiment now? Let's try it out. So V and T is changing, pressure is constant. Let's go to this thing and see. Okay, let's reset this thing again. So we are changing volume and temperature. So we're going to keep our, what we're keeping constant, pressure constant. Okay, let's get some gas inside here first. I think this is enough. Okay, let's keep pressure constant. Now, let's see. The pressure is currently at about 1500 kPa. What happens when you add heat into the gas? See, this fire pot here. If I add fire, why suddenly the volume can increase one? That's because when I add heat, the particles are moving faster and faster, more kinetic energy. So they will hit against the wall more. So in order to keep the same pressure, because you say you want to keep pressure constant, right? The volume have to expand. You see? Oh, cannot now. Volume is too large. Okay, never mind. I cool down the gas, I put ice. Let's see what happened. Oh, it's a bit slower leh. Change liao. Okay, let's keep pressure constant. Okay. So if you put ice cube, the gas particle lose energy, they move slower. To maintain the same pressure, your gas have to shrink. Okay, so that is the whole idea of what this Charles' law is about. Volume and temperature is changing. Let's write that down. So the experiment that they did here is when you heat a gas, what happened to the temperature? Temperature increase, and then the gas particles move at higher speeds because they have more kinetic energy. Okay, so I'll put here KE increase. So for the pressure to remain constant, because now they are move faster, they hit and the bigger force, hit the walls again, bigger force. So for the pressure to remain constant, what does the gas have to do? The gas expands. That's why we see the volume just now get bigger and bigger. Okay, so that the rate of collision between the particles, rate of collision of particle and wall, this is an N, is constant. Oh, already said remains constant. Oh, rate of collision of particle and wall of container is constant. Now you might be wondering, Miss, what happened if the volume cannot increase leh? Well, you see lor, you try the experiment. What if I keep it here? Okay, this is about 500, 600 kilopascal. What if I increase the kinetic energy, I add fire, but then I cannot increase the volume? You see what happened to the pressure? Pressure going up lor. You see the thermometer up there? The thermometer also going up lor. So thermometer increase, pressure increase. Okay, so that is another experiment. But for now, we are doing Charles' law. So we will say, okay the volume have to increase. Pressure constant ma. So how would we summarize that in a relationship? So we know that when your temperature increase, the volume have to increase in order to keep the pressure constant. So you can say, increase. So this is proportional. V proportional to T. Now I need to warn you, the temperature here all must be in Kelvin. No more Celsius. It's all absolute temperature now, so Kelvin. So from here, you can come up with the relationship between two states, the beginning, initial, and the final. And that will be V1 over T1 equals to V2 over T2, because V over T equals to constant ma. So this is the relationship of Charles' law between two states of a gas. Note this only for ideal gas. So in this case, pressure is kept constant. Okay, so if you want to plot a graph, how to plot that? We do the same thing like before. So first, let's plot our VT graph to see how it will look like. So if we just plot V against T on this axis, VT is a straight line because V proportional to T ma. So very nice, you can draw straight line. Zoop. Yeah, almost straight line lah. Okay lah, something like that. Okay, I changed it. So that's the first one. And if you have a certain change in state, okay, maybe you start off at a low temperature here, in a small volume, so V1, T1, and then you increase the temperature of the gas. So there's a heat transfer. So now you're at a higher temperature, but you also have to be at a higher volume to maintain that same pressure. Okay, this is how the graph would look like. But also, we're going to draw our classic PV curves. Okay, so if we draw PV, it's the same thing as just now here, but now we actually know what the curves are. So if we remember the original PV shape, right, it's something like this, right? Let me try to draw the dotted line for you. So it's something like that, okay? Two inversely, two reciprocal curves. And the first one is at a lower temperature, right? Throw back to this one. Lower temperature, higher temperature. So here, now we can think of it this way. If down here is, let's say, the first lower temperature, T1, you increase up to a higher temperature. But what are you keeping constant? Pressure, right? You see up here? Pressure is constant. Means the only way you can draw this PV curve line thing is from here, straight line, to here. Either to the right or to the left, I don't know. It depends on whether your volume is increasing or decreasing. Okay, so in this way, you have a constant pressure. P constant, yeah. But your temperature is changing because you're going from one to the other. Okay, so this one is a little bit interesting. So you're gonna have, let me change this to green color. So for initial temperature, you can be at a certain volume here. And at a higher temperature, you will be at another volume, V2. Now the reason why we want to draw PV curve is so that we can find the work done, because area under the PV curve is work done. So that's why for all the laws, we want to draw PV curve as well. So this shaded area right here will be the work done in the process of changing this gas temperature and volume. Okay, so that is one thing lah, huh? Now notice work done only happens when there's change in volume. Otherwise there's no area under the graph. Okay, here got change in, here got area under the graph. Here got area under the graph. We'll see the next one whether got work done or not. Okay, so this is the first one. Okay, the last law that we need to look at is pressure law. Miss, we changed pressure. Yes, but what else are we changing? What have we kept constant so far? If you look at your handout, what have you take notes? We have kept temperature constant. We have kept pressure constant. I guess the third one is to keep volume constant. So I write here first. Volume is constant. Also, the number of moles is constant. So what are we changing? Let's write on top. The only thing left to change is pressure and temperature. So now we are going to play with pressure and temperature. We add temperature, we see how pressure change. Okay, let's do experiment. Reset again. Now we need to throw in some gas. And we want to keep volume constant. So we fix the container. The container cannot get bigger or smaller already. Okay, we're going to wait for the gas to spread out. Come on, guys, hurry up. We are waiting for you to spread out, to stabilize a bit. Okay, so now what we're going to do is, we're going to do what people did in the past. So they put in gas, then they heat the gas, and they see the thermometer and see the pressure gauge, which is this one right here. So let's add some heat, and let's see how the pressure changes. Okay, so I'm going to add heat. You watch the thermometer. Okay, thermometer up here. You see the Kelvin. Kelvins are increasing 500, 600, 700. Now you look at the pressure gauge over here. What happened to the pressure gauge? It's going up. It's going up. It's going up. Now I want you to pay attention to the particles. They're moving faster and faster, you know. Let's see what happened when the pressure hit maximum. Oh yo, the lid explosion now. Pom pom. This is also why they say do not place gas can in a hot environment because it heat up, pressure increase, pom pom, explosion. So this is what happens, okay? You add heat, temperature increase, pressure increase, explosion. So that is what we need to write in our notes. That is the pressure law. So what's the story? What did you observe just now? Let's write it down. When the gas is heated, its temperature will increase. More kinetic energy ma. So what happened to the gas particles? They move faster. Because, you know, kinetic energy increase. Put a reminder here. Ke increase. So since the volume of the container is fixed, by experiment we choose that to be fixed. So if the volume is fixed, what happened to the gas particles? As you observed just now, the gas particles will collide more frequently. Because they're moving faster, they collide more frequently with the walls of the container now. So, what happened to the gas pressure? Collide more, I hit you, you hit me. Gas pressure will increase, lor. So if you thought that was fun, I highly suggest you go to the simulation, play with it, walk in the footsteps of all these people that did gas experiments once upon a time. All they did is just heat up stuff, watch it explode, increase pressure, pump in more stuff. You get the point, okay? Final notes about moles are, if you notice at the beginning, I pump in a certain amount of gas, right? Let's return the lid. Come back, lid. Okay. The beginning, I pump in a certain amount of gas. So that will determine the number of moles in this container. And that's fixed already. Okay. I don't pump in any more gas. I don't let out any more gas. Okay. So just heads up on the moles stuff. So this is talking about pressure law. What is the experiment behind this? So how can we create equation or some equations to relate pressure and temperature? So we know from experiment that when you increase the temperature, what happens to the pressure? Pressure will also increase. So increase, that means P is proportional to T. Proportional. Oh, the temperature must remind you. This T is in kelvins. No Celsius. No Fahrenheit, no Celsius. Stick to Kelvin, absolute temperature. From here, we know P over T is a constant. Because P proportional to T. So we can equate them and say, for a change in state, P1 T1 equals to P2 T2. And this is the equation that you can use for calculations in all these kind of gas-related problems lah. Okay. Suddenly you increase the temperature, what is the new pressure? In the morning, your tyre is this pressure. At the night, it's colder, right? What is your tyre pressure? That's what they'll ask you. So here, V is constant. We are keeping the volume constant. Now, for the last part of graphs. So if we want to plot a graph of P against T, that will be a linear straight line, very nice graph also. So maybe you start off with a lower temperature. What's my initial temperature? Purple. Okay, so let's stick to that convention. So maybe you start off at a low temperature. You have a low pressure. Okay, so this is T1 and P1. Then you increase the temperature already. You see the fire there burning. So when you increase the temperature, the pressure will also increase proportionally. 2 times temperature, 2 times pressure. Temperature in Kelvin. Must keep reminding you. Pressure 2 times. Okay, so that is how you can think of changes. Either increasing temperature or decreasing temperature, same thing lah. And also, we want to study this PV work done. We want to know the amount of work done in this process of increasing the temperature and seeing the pressure change. That's why we need to draw PV curves again. So something like that, okay? So we are changing what? Temperature. So you are going from one curve to the next. Maybe this first curve is a lower temperature. Second curve is a higher temperature. So you want to increase temperature. But what is constant? Pay attention, top right. Volume is constant. Oh, so how will you draw the thing? Well, this means your graph will look like this. Very weird one. If you increase temperature, then you draw like that lor. If decrease temperature, then your arrow is the other way lor. Up to you. But notice, what is the work done for this graph? You scratch your head and think, see, what's the work done? In the previous example, we said work done is area under the graph. But what is the area under the graph here? Confusion. So you see, here got area under the graph. Here got area under the graph. But what is this one? Confusion. So here there's actually no work done. So I will put a star here. No work done because no area under the graph. So there's no change in volume of the gas. But what we do have though is a change in temperature. So maybe your first temperature is down there. That will correspond to a lower pressure. Then when you increase the temperature, you will be at a higher pressure. Right up here. Quite interesting, huh? To study all these temperature, pressure. So yeah, a lot of people last time did all this experiment. Okay, quick note. I will clarify here that temperature 1 is smaller than temperature 2 lah, huh? In case you're wondering. Okay, so that is all 3 laws put together. All the experiments that people did on gases and what they discovered out of that. Okay, to end this video, we are going to go to what we call the ideal gas equation. What if there was a way to combine all these laws together? Can? Can. This is what we call the ideal gas equation. After all these laws just play with PV and T, right? So there should be a way we can combine them. So people came up with what we call the ideal gas law. So the thought process goes like this. Since pressure is proportional to temperature, but also pressure is proportional to what's the other one? Volume, right? 1 over volume. Okay, so we write here 1 over V. So if you combine these two ideas together, you can say and conclude that therefore pressure is proportional to temperature over volume. That is the basic idea of our ideal gas law. So if P proportional to T over V, that means I can say, so PV over T is constant, no? Constant. I don't know what constant to say, so I just give it an alphabet. Let me just call it K. Never mind, I say constant. Okay, so this is the basic idea of where the ideal gas law come from. People say, too many equations, we combine into one. Okay, combine into one. So the ideal gas equation, the main one, looks like this. PV, the T, they move to the other side, right? Constant. Now the constant, what is that constant? That is what we call nRT. The T we move to the other side. So the constant is our friend here. Constant. Now what is all these symbols? P, we know is pressure. V is volume of the gas. N is the new one. Let's label it here. Okay, so our N here is the number of moles. Okay, moles is another way of measuring how much substance there is, how many gas particles are there. R is another one that is known as the universal gas constant. This is a constant people experimentally determine one. So you can go to your calculator and look for R, you will know the value, or you can look at the exam sheet right in front, you will see that it's 8.31. Temperature, of course, is just Kelvin. Must remind you again, Kelvin only, in units of Kelvin. But if you're thinking about what's the unit of the moles, so number of mole is mole long. 1 mole is 1 mole. Gas, universal gas constant has a unit. It's a little bit more strange. It has many units. But this one unit is J mole -1, K -1. Joules per mole per Kelvin. Okay, this is our ideal gas law. Woo! There is also actually another form of it. But pause first, I will show you the other pattern of the ideal gas equation. We'll come back to it after we look at what is an ideal gas. So with this equation, people decide we need to decide what we actually call ideal. Ideal versus non-ideal. How we know? So of course, people decided that they will call ideal gases all the gases that obey the relationship that we looked at just now. So what is the relationship? Let's write it out. So this will be the relationship where P times V over T equals to a constant. And no matter how you change P, something else must change so that this is still a constant. The ratio PV over T is still a constant. Okay. If you change temperature, pressure or volume have to change. So there will always be two things changing here. Then only you can call this an ideal gas. Does it exist in real life? Actually, we haven't really found a perfect ideal gas yet. But there are gases that are very close to ideal in certain situations. Okay, so this is what we define an ideal gas. Next time people ask you, what's ideal gas? You say, nah, gases that obey the relationship. If you change one thing, of course something else has to change lah. So I mentioned earlier that there is another pattern for this equation, right? I will show you both. Okay, so people in chemistry come along and they're like, I like to think of it in other ways. Can I think of this equation in other ways? So yes, there is this thing. Also, Mr. Boltzmann came up with this thing called the Boltzmann constant. I think it's Boltzmann, one N to N. I can't remember already. But Boltzmann constant is what we call KB. Okay, and this thing equals to R over NA. You're like, what miss? What is all this? R is the universal gas constant, the same R up there. NA is another thing thanks to this guy called Avogadro. So this is the Avogadro constant. And you're like, miss, what is this? So Avogadro constant is just saying the number of particles in 1 mole. If you take chemistry, this will be kind of familiar to you, hopefully. So number of particles in 1 mole of gas. And the number of particles will be is a constant. So 6.02 times 10 to the 23. So 1 mole should have this many particles. Okay, if you think of I lost my simulation already. But you think of all the little blue color particles that were flying around. If I say there's 1 mole of gas inside there, means there's this many particles inside there. So the Boltzmann constant is defined this way, and you can sub that R into the top equation. So we can say PV equals to N times R will be now KB times NA times T. Okay, so there's another way to simplify this thing. Okay, so PV equals to what we say NkBT. B is a subscript. So this is the other form of the equation based on the number of particles. Because I should add a little note here. Because the number of atoms is N. Number of atoms N, this is the way we define things, okay, is the moles times the Avogadro constant. Okay, because if you're wondering like, miss, how am I going to remember this? Don't remember lah, you kind of know the two equations can already, okay? Because the Avogadro constant is per unit mole lah. So how many particles per mole? So this is the unit of particles per mole. Number of moles, the unit is mole. Up here lor. So if you multiply mole times particles per mole, which is this thing, then you get number of particles or number of atoms or number of whatever lah, okay? So this one is this thing right here. So we simplify it to that. Okay, so that is the whole idea of ideal gases, ideal gas laws, and where they came from. I would say don't worry too much about the small details. Just make sure you try out some past years. You know how to use the ideal gas law, which is basically Boyle's law, Charles' law, and pressure law combined together. One student once said, miss, isn't there a coleslaw also? Coleslaw eat in KFC lah, not for gas, okay? So this is the introduction to gases. Go try out some of the past year questions and check out the examples video that come after this to see how you can apply these equations to think about states of changes of gas, okay? You increase pressure, what happened? You increase temperature, what happened? You keep the volume constant, what happened? Okay, all these kinds of things. That's all for this video. I will see you in the next example video.